everybody. In this video, we're going to talk about the addition algorithms for whole numbers. So as I teach you the algorithms, I'm also going to show you some models that you can use to help your students understand the concept behind why we add whole numbers the way that we do. So my favorite model for helping students understand the addition of whole numbers is to use base 10 blocks, because this gives students a visual picture of what the number means. So when you're first teaching your students multi-digit addition, you're going to want to start with a problem like this one that doesn't involve any carrying or any regrouping. And to visualize this model and help your students conceptually understand it, you'll first visualize each of the numbers separately. So you'll say, okay, well, 1,214 is going to have one thousands block, two hundreds blocks, so I have two of those, then I have 110, and then I have 4 ones. So here's 1, 2, 3, 4 ones. Then we'll say, okay, well, the second number has 3 hundreds, so I'll make 3 hundreds in this group, and 2 tens, and 5 ones. So here's 1, then 2, 3, 4, 5. And so this is basically visualizing the two numbers separately. And then addition means that we're going to combine these numbers together. And so we say, okay, well, if I combine these 4 ones with these 5 ones, then all together I'll have 9 ones. And so we'll put a 9 in the ones column. Then if I have 1 10 and 2 tens added together, that's going to be 3 tens. And if I have 2 hundreds and 3 hundreds added together, that will be 5 hundreds. And 1,000 plus nothing is just going to be 1,000. And when your students are figuring this out, they may not necessarily add the ones and then the tens and then the hundreds. They may add the hundreds and then the tens and then the ones. And this is why you want to start off with a problem like this, where there is no regrouping, so that they understand that they're just combining the place values together. Then, once you feel like they've really understood this, then you can move on to more complicated problems like this that do involve carrying or regrouping. So this problem could be visualized with 1,000, 600s blocks, 2 tens blocks, and 8 ones blocks, then 500s, 4 tens, and 3 ones. And if we're going to add these numbers together, your students, especially if you're using physical blocks and they're doing it by hand, they might add all of these together, combine them all up, and then they'll recognize that when you put 3 ones together with 8 ones, you have 11 ones, and there's enough ones that you can make this simpler by regrouping the 10 ones together, which makes 1 10 and 1 1. So it's still the same number of blocks, but you're just converting them into a simpler type of block. So you just have 1 tens block instead of having 10 individual ones. And then they'll also notice that when you combine the hundreds together, those can also be regrouped to make a thousands block. And so when your students do this math problem with the blocks, they'll realize that the answer is 2,100, 6 tens, and 1 1. And then you can kind of build off of that to help them understand how they can do the problem even if they don't have the blocks. But it's important that they conceptually understand why the answer is the way that it is before you necessarily go into solving all of the algorithms. So after your students have a visual picture of what addition means and the fact that sometimes you're going to have to regroup some of the blocks into a bigger block, like say like 10 hundreds, regrouping those into 1,000, then you can move on to teaching them the standard algorithm. So when you're teaching them the standard algorithm, which is basically like how we write out the process of solving multi-digit addition, it's helpful if you go in 3 phases. So in the first phase, you're just going to focus on each place value one at a time. So you say, okay, if I have 6 ones plus 9 ones, well, that gives me 15 ones. And if they played around with the blocks enough, they know that 15 ones can be regrouped into 1 10 and 5 ones. So you just write that down. Then you say, okay, well now let's add together our tens. Well, if I have 5 tens plus 8 tens, that's 13 tens. But because I have more than 10 of the tens, I can regroup 10 of them together to make 100, which gives me 100 and 3 tens. And then I have 0 ones because I was only working with the tens blocks. Then you say, okay, well, if I have 3 hundreds plus 2 hundreds, that's going to give me 5 hundreds. And you basically write out the steps for each place value in a different line. And then you say, okay, well, this is how much we have from each place value, but how much do we have all together if you include all 3 place values? And you say, okay, well, if I add all of these together, 5 ones plus 0 ones gives me 5 ones. 1 10 that came from regrouping my ones, and 3 tens that came from adding together the 5 and the 8, that gives me 4 tens. And then 100 and 500s makes 600. And as you're teaching this, you'll want to kind of correlate it with the blocks. So like you would have the blocks either like on your iPad that's being projected on the screen, or you could have like physical blocks. And as you were manipulating the blocks, you would show the students how you write down each step of the process. And then once they're kind of getting that, then you can move on to the intermediate algorithm 2. So the way that intermediate algorithm 2 works is it's very similar to the first one, where you're just focusing on each place value individually. And you say, okay, well, 6 ones plus 9 ones is 15 ones. So I'm going to write down a 15 where the last number is in the ones column because I have 15 ones. Then when I add together my tens and I say, well, I have 5 tens plus 8 tens, that's 13 tens. So I'm going to write down a 13 where the 3 ends in the tens column because that's what I was adding up. And so the last step would be to say 300s plus 200s is 500s. So I'll write a 5 in the hundreds column. And then you wrap it up in the same way where you say, well, if I have 5 ones in the ones column, that's 5. 110 plus 3 tens in the tens column is 4 tens. 100 plus 500s equals 600s. So notice that it's almost the same as intermediate algorithm 1. The difference is that instead of writing the zeros to communicate the place value, we're helping the students realize that the columns themselves can communicate the place value. Then once they're doing well with this, which it should be pretty quickly because it's not that big of a transition, then you can move on to the standard algorithm. And you can say, it would be really nice if we didn't have to write out like 4 lines of math to calculate this, but rather if we just took little notes for ourselves. So we could say like 6 plus 9 is 15 ones, and 10 of those ones can be converted into a 10, and 5 of them will stay in the ones column. So we're going to put a 5 in the ones column, and then carry a 10 over to the tens column. So we're going to write a 1 in the tens column, and we're just going to add all of the tens together all at once. So 8 tens plus 5 tens will be 13 tens, just like with intermediate algorithm 1 and 2, but we're also going to add the extra 10 that was carried. And so that makes 14 tens, and 4 of them will stay in the tens column, but 10 of them will be converted into 100, and we'll have 1 extra 100 in the hundreds column. And then 100 plus 300s plus 200s equals 600s. And you can show your students how this standard algorithm is shorter to write out than either of the previous intermediate algorithms. But when you're teaching it to your students, you don't want to jump straight to the standard algorithm, because if you jump straight to that, it can be a little bit harder for them to understand why they're writing a 1 in the tens column. But if you lead up to it with the intermediate algorithms and then you teach the standard algorithm, it will help them understand it a little bit more clearly. And after the students have learned the standard algorithm, you still want to do more problems with them where you're visualizing the process so that they can visually tie the concept to the numbers and the processes that they're writing down. So what this would look like, if we go back to that old problem we were working on where we have 1,628 plus 543, we would say, okay, well, we always want to start with the smallest place value. Like before we learned about the algorithm, you could have added the hundreds together and then the tens and then the ones. But since we have learned about the algorithm, we know that the smallest place value is the best place to start, because some of the ones might need to be regrouped into tens, which changes the number of tens. And if the tens have to be regrouped into hundreds, that changes the number of hundreds. So it's smartest if we combine the ones first. And so we'd say, okay, well, if I combine all of these ones together, how many ones do I have? And your students will say, oh, like we have 11 ones. And we regroup them and it shows visually, yeah, we have 1 10 and we have 1 1. So we're going to put a 1 in the ones column and carry a 1 to the tens column. Then we're going to take this 1 10 that we're carrying plus these 2 tens plus these 4 tens. And if we combine them all together, so I'll bring these 4 up here, and we put them all together, then how many tens do we have? And the answer would be that we have 7 tens, because we have the 1 we carried plus the 2 plus the 4 tens from the problem. So we have 7 tens. Then we'd say, okay, well, if I take these 6 hundreds and add them to the 5 hundreds, how many hundreds do we have? Well, we have 11 hundreds. And since there's more than 10 of them, we can regroup these together into a thousands block. And we can say, okay, well, in the hundreds column, I have 100. And then I also have 1,000 from the hundreds that got regrouped. And then 1,000 that I regrouped plus the 1,000 from the problem gives me 2,000. And my answer would be 2,171. And this is really good, and you can just use base 10 blocks if you want to. But if it's feeling kind of clunky to have all of these blocks, especially if you're using physical blocks, you can transition to using a chip abacus. And this can be helpful for having the students do the process versus like you displaying it up on the board, because a chip abacus is much more easy to work with. And another model that you can use that is very helpful when you want to have students work on their own and practice it by themselves is the idea of a chip abacus. Because with the blocks, I personally like using an iPad the best and displaying it because it's just easier classroom management wise to just show it up on the board. But if you want to have students working on their own, if you don't have a base 10 blocks set for all of your students, or if you don't want to get them out because that's going to take up too much time to manage all of that, you can have students use a chip abacus, which basically means that you're going to have a piece of paper that has all of the different place values in it. And then on the piece of paper, you're going to have little poker chips that represent the blocks. So I would recommend color coordinating your poker chips. So like you have yellow poker chips for the ones blocks if the blocks you've been using are yellow for the ones blocks, and then green ones for the tens and so on. And basically what you'll do is you'll say, okay, well, if we have 8 ones plus 3 ones, they'll have the little poker chips for those. And you'll say, okay, well, since there's 11 ones total, I can take 10 of these ones and regroup them into a tens poker chip. And if they've seen this with the base 10 blocks, this transition should be pretty easy for them because they're like, oh, the green ones represent 10 blocks, the blue ones represent hundreds, and so on. And then you say, okay, so I have a 1 in my ones column. And so that's how you would show them that this needs to be a 1. Then you say, okay, when I add together all my tens, I have 7 tens, which isn't enough to make 100. And so I'll just write a 7 in the 10 spot. And then you'll add together your hundreds and you'll say, okay, if I have 6 hundreds plus 5 hundreds, that's 11 hundreds, which is more than 10. So I can take 10 of these and convert them into a thousands chip. And that leaves me with 100, and then I have 2 thousands. And so that's how you get these two numbers here. And so the chip abacus is basically just like a more generalized or abstract way to show the same process as the base 10 blocks. And you don't actually even have to do poker chips. You can also draw pictures, kind of like what I showed here. So this could even be something where the students draw out on their papers the different place values and then like how many dots are in each one. And then they can kind of show this regrouping similar to how I did. It's usually a little bit easier if they're physically manipulating it, but you can also do it just by drawing out the dots instead. So that's another model that you can use to help students understand why we add together the place values the way we do. And there's another algorithm called the lattice method that a lot of students find even easier than the standard algorithm. So with the lattice method, you add together each place value and you don't worry about carrying any numbers because the way the lattice method works will carry the numbers for you. So basically the way it works is you say like, okay, 6 plus 9 is 15. So I'm going to write a 1 and a 5, but I'm going to separate them with this diagonal line where the bottom number is like the ones and the top number is the tens. And if you're modeling this with blocks, you can tell the students like these are the number of blocks that didn't get converted into the next place value. And then this is the number of blocks in the next place value. So 6 plus 9 equals 15. Then you say 5 tens plus 8 tens is 13 tens. And again, the 3 is the number of tens that didn't get regrouped. And then this 1 was the 10 tens that became 100. Then 3 hundreds plus 2 hundreds is going to be 500. So I put a 5 here. And it can be helpful sometimes to put a 0 here because there were 0 hundreds that got regrouped into thousands. And once you have all of this written out, then you just add them up diagonally. Because this 5 was the ones that didn't get regrouped into tens. So you're just going to have 5 ones. This 3 is the tens that didn't get regrouped into hundreds, but it's going to be combined with the 110 from the ones column. And so that makes a 4. And then 500s plus the 100 for here and here would make 600. And so the process is basically that you like add up along the diagonals, and that takes care of the carrying process. And you'll notice that this is very similar to intermediate algorithm 2, because that's basically what intermediate algorithm 2 is also doing. It's just writing it out in a different way. So some of your students may prefer the lattice method over the standard algorithm. So it can be helpful to teach both methods and then let the students decide which one they like the best. So that's the addition algorithms for whole numbers. If you have any questions, let me know, and I hope you guys have a great day.